Hey there, and welcome back. So, this is going to be the last episode about Commodore 64 scrolling. Now, before we start today, I just gotta say a few words real quick. I'm gonna be honest with you, I'm not the best programmer out there. I'm not the best programmer for the Commodore 64. There are probably thousands of people who are better than me at programming the Commodore 64. That means that what I'm going to show you today is not going to be the perfect, most optimized code for scrolling. But in a way, that's a good thing in this case. Because the point of this channel is not to brag or anything like that, but it's to help people get started programming the Commodore 64. And I feel my job is to make this as easy as possible to lower the threshold for getting into programming the Commodore 64. So hopefully that's what we're going to do today. Hopefully the code will be fairly easy to understand, at least as easy as possible. So another thing, we're gonna talk about raster interrupts today. Now, if you haven't watched my video about raster interrupts, or if you don't know what raster interrupts is, I recommend you start by watching my video about raster interrupts, because otherwise this can get a little confusing. So let's get started. And let's start by doing a quick repetition. So this is from the first episode about scrolling, where we looked at this thing where we can hide the borders. We looked at that quite a bit. Just by changing this bit in D1016, we can hide the borders, which is going to help us with the scrolling thing, make things look good. And we have also seen that we can adjust the screen like that, pixel by pixel. And again, that's going to help us do scrolling. Now, I have to say something. In the last video, I said something wrong. I said when we were scrolling the screen left, I said the counter here was going from 0 to 7 all the time. That would be true if we were scrolling to the right. But since we are scrolling the screen to the left, it's going from 7 to 0. 7 to 0. So it's going to from 7 to 0 all the time, because we're starting with the screen adjusted to the right like that. And in the last episode, we talked about this camera system, that we need to have some sort of camera system that's going to pan across the level. And we're going to take a closer look at that today. But since I'm correcting myself here, I need to correct something else. And by the way, I'm sorry about this, but the code I briefly showed you in the last video, I scrapped that and I made some new code from scratch. So I hope you weren't paying too much attention in the last video, because I threw that code away and I made something new, which we are going to look at today. But here in CharPad, when I have made my level like this, so I said that we need to go to File, Import, Export, Binary, and Export Map. And that's true. That's exactly what we need to do. But something else that I didn't tell you in the last video. When we're exporting the map like this, we're exporting the just the graphics, just the screen codes, the characters like this, laid out like this. But we're not exporting the colors. So what we're going to do in this example, we're going to go to File, Import, Export, Binary, and in CharPad there's a function here called Export Color Map, per map, char cell. So this option here, Export Color Map. And what that's going to do, it's going to export the map it's going to export the colors in the same way that it's exporting the map like this. So for example, this color and this color and this color and this color is going to come in the same order as the characters, which means that we will end up with something like this. We are exporting the map like this, laid out like that, and we are exporting the colors the same way, so that the colors correspond with the screen codes in the map file. So we have two files, the map file and the color file. And the way that we export these files is going to help us a lot when we're going to do scrolling here. So hopefully you can see the point there. For example, this cloud, if we go down here to this color file, it's going to say white somewhere around here where that cloud is. So they correspond perfectly like that. And of course I made this purple because to show you that we are not exporting the colors when we are exporting just the map graphics. Whoa, alright. Okay, there we go. Alright. So, just to make sure that we know that when we're making this map, we choose export map and export color map. Two files for our purpose today. But before we start looking at the actual code here, we have to talk about something else. Something that we haven't really talked about before. That's performance. Now, I purposely avoided talking about that in the Commodore 64 course because, especially in the beginning, it can be kind of confusing. When you're learning this from scratch and everything is new and there's so much to remember, we don't have to talk about performance then. But now we have come to a point where we have to talk about this, because scrolling on the Commodore 64 is very CPU intensive. So we have to make the most efficient code possible. And we have to understand how this works. So we have to talk about cycles. So what are cycles? Well, cycles is just a measurement for time. So how fast things work in assembly language. So let's start by looking at some mnemonics here. This is the website for showing the mnemonics for 6502 programming. So if we, for example, go to our good old LDA mnemonic, load accumulator, that's just one sort of command, if you can call it that. So how much time does it take for us to write LDA? You know, how can we measure that? Well, unfortunately, it's not super easy and straightforward, because if we take a look at this table here for LDA, there are a lot of different things here, but we have different modes for the different mnemonics. We have this thing called immediate mode. What's that? Well, immediate mode, that's when we're loading an actual number. So when we're using the hashtag in front of a number, which means if I say LDA hashtag 4, that means load 4, the number, actual number 4 into the accumulator. And in this case, we're loading the hexadecimal number 44 into the accumulator. So, and the different modes. If I write LDA without the hashtag, LDA, just a $44, load A with the hexadecimal 44, that's not loading the number, because I don't have this hashtag in front of it. What I'm doing here is I'm loading from memory address 44. So whatever is in that memory address, I want that into the accumulator. And in this case it was the 0 page, but this would be how we normally would do it from a regular memory address. Load A with whatever is in memory address 4400. Now, the point when we're talking about cycles and performance here is that the different modes can have slightly different performance. So here we have something called len, we have something called TIM, length and time. Now, length here, that's just how many bytes one of these mnemonics takes up. So, for example, if you take LDA here in immediate mode, which means we are writing LDA with an actual number, how much space is that going to take up in the memory? Well, it's going to take up 2 bytes if we write it like that. Okay, so what about performance? Well, it's going to take up 2 cycles, 2 CPU cycles. And if we load LDA with, let's take this one, when we're loading A with something from this memory address, then it's going to take up 3 bytes in memory. Just this one command is going to take up 3 bytes when we write it like that. And it's going to take up 4 cycles. So twice as slow as just loading A with an actual number. So when you write LDA like that, it's going to take up 4 cycles. So now, if this is the first time you're hearing about cycles and performance, stuff like that, this cycles thing probably doesn't make much sense. So what we need to do right now is to put this into some sort of context. Okay, how much is a cycle? Is it a second? Is it a minute? You know, whatever. We need to put this into context for the Commodore 64. And let's start by looking at a picture. So here we have a picture that I took from a site called dustlayer.com. Unfortunately, that's not up. That site is not up anymore. But anyway, here's the picture. So there are a lot of numbers here. We don't have to go into detail about all of these numbers. But let's start by looking at what's a cycle. How fast is one cycle? Well, remember, the Commodore 64 was made when we had the CRT televisions, and they were drawn with this scan line going across the screen all the time. There's this little dot of light. So starting up here, it's going to go across the screen over and over again until it goes back up and start drawing again. So a cycle, if we imagine that the scan line is right here now and it goes across the screen, and if you can see this M here, one cycle is just one part of this M. So let's see, it's just drawing part of that M for this amount of time. That's how fast a cycle is. So again, this can be a little abstract, little difficult to understand at first, but the main point here is that one cycle is super fast, because just one frame on the Commodore 64, just drawing one frame, for us as humans, that's super fast. And this is not just a frame, it's just a tiny little part of that frame. That's one cycle. And let's look at this one. So it says here 40 cycles. So it takes 40 cycles from here on the screen to over here. That's 40 cycles. And just to put this even more into context, how many cycles do we have, or how many cycles are there in a full frame update? So just displaying one frame on the Commodore 64, how many cycles are there in there? Well, it's a little difficult to give 100% accurate response to that, because there are several things that we don't need to talk about right now, but let's say that it's slightly below 20,000 cycles. A little below 20,000 cycles for a full frame. So 20,000 cycles. So which means that we do have quite a bit to work with. But 20,000 cycles, that's not unlimited. That's not an unlimited amount of time. So we still have to make this code efficient. And in fact, we need to make sure that our code is going to run when the screen is not being updated. To explain that more closely, we need to look at another picture. So, like I said in the beginning, you probably should know about raster interrupts to understand this episode fully. So what I've done here, this is just a screenshot. What I've done here is that I've enabled raster interrupts to trigger at line 250. That's here, where this yellow part starts. So what I'm doing here is that the border color for this game is black, but here at line 250, I'm changing the border color to yellow. And the reason I'm doing that is so that I can see how long my scrolling code is going to take. So the border color is black, but here at line 250, I change the border color to yellow, and then I start my scrolling code. So it starts here, and it works all the way down here, but it's not done when the frame is over. So on the next frame, it continues up here, and then it keeps on working, and it's done here. The scrolling code is done over here, and then I changed the border color back to black, which means that this yellow area that we can see in the border, that's how much time my scrolling code takes. So this is a little unfortunate because what's happening here is that the scrolling code is not done when the screen starts to draw the background up here. Now the problem with that is that in my scrolling code I'm updating colors. So I'm gonna be honest with you, I cheated a little bit here. So I cheated by moving the clouds down here, which means that we're not gonna notice anything here because we don't have to update too many colors up here. And by the way, this sun that we see up here, that's just a sprite. So that's not affected by this. But my scrolling code stops down here, which is after the screen has started to draw or the graphics or the colors. Now, the one of the things that we could have done here was to make a HUD. So we could have had a HUD area up here where we could display score, player lives, stuff like that. That's one way to solve this. And in fact, if you look at games on the Commodore 64, a lot of them, maybe most of them, have some sort of HUD, either at the top of the screen or at the bottom of the screen. So it's a little ambitious to make a full screen scroller like this, what I did here. Because, like I said, scrolling is really CPU intensive. And I tried to make a pretty efficient code here, but still it's not fast enough to complete before the screen starts to draw up here. So, like I said, a workaround could be to put a HUD up here, or, you know, not have a full screen scroller. So, all of this is just to give you some sort of feeling about performance and how this works, and how CPU intensive a scrolling routine like this can be. A full screen color scroller, it's very CPU intensive. But like you probably saw in the intro for this video, when we run this, it looks fine. Because, like I said, I cheated. I don't have any colors up here. It's just this background color here, this extra color. So we don't have to do a lot of work with that. So what takes up so much time here? Why does it take so much time? Well, it's because we have to update most of the thing here is that we're updating the colors. And as you remember, a full screen on the Commodore 64, that's 1,000 characters, which means it's also 1,000 colors, or 1,000 color values, if we need to update every single character on the screen. So that's 1,000 bytes that needs to be updated in a flash. So the problem here is that, like I said, if we make this too slow, if this is not efficient enough, then we're gonna see something like we saw in the last episode, where it's kind of jerky, the colors are wrong, stuff like that. So just to drive home the point here, let's look at this screenshot from Green Beret. As you can see, they have a HUD up here with lives and score and stuff like that. And at least in this screenshot, there's not a whole lot of stuff going on here. So, like I said, it's maybe too ambitious in the beginning to make a full screen scroller, but I wanted to do it anyway just to show you how this would work. But like I said, keep in mind that doing a full scrolling routine is CPU intensive, and it's probably a good idea to split the screen to not update the full screen like this. So finally, here we are looking at the code. And by the way, this code is something that you can download from my website, and the link is in the description. So the way I've set this up is pretty much like I've set up all my projects and how things are done in the Commodore 64 course, which means that we have several files and have these include files and stuff like that. So you know how the project is structured. So I just start, like I do always, with initializing the system stack. And I just like to do that because, yeah, just to be safe. But then I start this code by jumping to subroutine system setup. Now system is this thing over here. And setup is of course this subroutine. So if you follow the course, you've probably seen something like this before. I'm disabling basic, and I set the screen RAM to 400, which is the default, but I set the character set to 3800 because I put a character set here at address 3800. That's where I put my character set. So I make sure to update that, and in D1016 I enable screen multicolor because my level is made with multicolor, and then I hide these borders. So I set the screen to 38 columns. I make sure to do that at the beginning. And here with the scroll bits, I adjust the screen to the right, which means setting these last 3 bits to 111, which means that we start with the screen adjusted to the right, so it's ready to start scrolling to the left. So make sure to do that here in this system setup. And then I just do some basic things like set the border color to black, the background color to black, and set the 2 extra colors, here light blue and brown. But down here I enabled raster interrupts. Now I haven't talked about raster interrupts in the previous scrolling videos because I didn't want to introduce some complexity unnecessarily. But now we have to talk about this raster interrupt stuff. So why am I using raster interrupts for this? Well, I mentioned it briefly earlier in the video. When we are updating the screen, and we've seen this before with sprites, when we're moving sprites around or changing graphics on the sprites, we don't want to do that at the exact time as the screen is being updated. Because if we move a sprite as the screen is being updated, we will get some sprite tearing, graphical glitches, and stuff like that. And the same goes here for when we're doing this scrolling thing and updating the background all the time. We need to make sure that all these things happen outside the update of the frame itself. So that's why I said earlier that it's a little unfortunate that my code is not done before the screen starts to update. So like I said, I had to cheat a little bit. But the reason for using raster interrupts, like I said, is that I can decide that at line 250, so just as the border starts at the bottom, so just as the background layer itself is done drawing, that's when I trigger the raster interrupt, and that's when I run this scrolling routine. So ideally it would be done before the next frame starts to update. And if we're using a HUD at the top, for example, then that would be fine. So what's happening here in this subroutine setup raster interrupt? Well, like I said, if you've seen the Commodore 64 course, it's pretty much the same thing. Let's not go into detail about all these technical things, but the important part here is that I set the raster interrupt trigger at line 250. So when the scan line reaches 250, bang, that's when we trigger our raster interrupt code. And what is our raster interrupt code? Well, it's what I have up here. Now I have some unnecessary debug stuff here, which is this and these things. Which basically just allows me to press a key on the keyboard, and then I can show that yellow area that we just looked at, or start and stop the music. So I'm just gonna remove that debug stuff, and then I'm left with this. This is what runs in my raster interrupt routine. So every time the scan line reaches 250, bang, we run this, which is in map this subroutine called scroll right. Scroll right. Oh, okay, well, maybe I should have called it scroll left. I was thinking that the camera was scrolling right, I think. Alright, a little confusing, but anyway, let's look at that subroutine now. So if you go to my map library here, then we have this scroll right subroutine. So here we get to the real magic of the whole thing here. So I start by checking D1016, this screen control 2 memory address. And then I mask it off by saying and have 3 ones here to the right, because I just want to check those 3 bits. What are those 3 bits? Well, those are the bits used for the adjusting the screen, pixel by pixel, like we've seen a few times now. So I'm just interested in those bits in D1016. And then I say compare that with just 2 bits there at the right. What's 2 bits there at the right? Well, if you read this binary number, it's 1, this is 2, 1 plus 2, that's 3, which means that we're comparing this with 3. Why am I doing that? Well, like I say here in the comment, scroll bits at 3. Remember, we're talking about these bits for adjusting the screen. And if the scroll bits are number 3, that means that the scrolling is at the half position across the screen. We can adjust the screen 8 pixels, and if we adjust from 0 to 3, that means that we are halfway done adjusting the screen. Why am I doing that? Well, when I'm halfway done adjusting the screen like that, that's when I want to load the graphics, the screen codes on the other screen RAM, the inactive screen RAM, so that when I've scrolled all the way to the left and adjusted the screen all the way to the left, and I'm going to switch over to the other screen RAM, then the graphics over there are ready, and I don't have to spend time loading those graphics there. They're already done. So I do that when the screen is halfway scrolled or halfway adjusted across the screen. 4 pixels across the screen. That's when I load the graphics to the other screen, so that's ready. Then I scroll the last 4 pixels, adjust the screen the last 4 pixels, and then I switch over to the other screen. Like I said, the graphics are already there, but I need to hurry up immediately after changing to the other screen RAM. Then immediately I have to color the screen as quickly as I can. Because I can't color that other screen RAM before I change over to that. We can only change screen RAM on whatever screen is active. Hopefully that makes sense. So when we're halfway done adjusting the screen, that's when I load the map graphics to the other screen. And as I increment this variable scroll X, which is the thing that keeps track of our camera system. So I increased that because the next time I'm going to load from the graphics file, the map file exported from CharPad, I need to make sure that my camera loads the next part of the map, and that's shifted over 1 character. This whole camera is shifted 1 character because that's the next part of the map that needs to be loaded in. So I increased that scroll X variable, and then I say load this scroll X variable, and I said and with 1 bit there at the right. Now if I say and with 1 bit there, that bit, so this bit is the number 1 in a binary number, and that's always going to be either 1 or 0. So if I say load the scroll X and it with that, that means that when I increase this number, this bit over here is going to go from 0 to 1 to 0 to 1 to 0 to 1 because of how binary numbers work. This is 1. If I want to increase scroll X to 2, then it would be like that, because this is number 2 in binary. Number 3, then it's this, and so on. So it's just how binary numbers work. And the point here is that if we just mask off this bit over to the right, then that bit is always going to be either 0 or 1. Why am I doing this? Sounds confusing, right? Well, basically I'm doing this because I want a system where I'm checking, is this an even number or an odd number? And based on if it's a 0 or a 1, and this, remember, this scroll X variable, that's going to increase all the time as my camera moves across the screen. We saw that last time. It's going to increase all the time. So based on what the last screen was the last screen a 0 or was it a 1? Based on that, I load either the subroutine called load map screen 1 or load map screen 2. So here I say branch if not equal, if I load scroll X and it with a 1 here, and I say branch if not equal. So if it's not 0, then we go to this label, which is down here. So when the bit in scroll X, this bit is 1, then we go down here and we load map screen 2, that subroutine. If it's 0, then we load this subroutine. So yeah, let's just look at those subroutines real quick now. And this is what I was getting at earlier when we're talking about performance. Now this is one of those things where you have to compare performance versus storage. How much space is this going to take up in a memory? And writing a code like this, LDA, SDA, LDA, SDA, LDA, SDA, it looks crazy, right? Because we usually do loops when we're doing something very similar like this. Just doing a loop with an offset, and we just run the loop over and over again. Now, doing a loop like that would be a lot slower than doing it in a brutal way like this, raw force. So it's much quicker to write a lot of LDA, SDA, LDA, SDA. It's much quicker than doing a loop. And like we talked about before, performance is super important when we're doing scrolling right now. So I'm just loading A with map row 0, y. I'm storing that in screen RAM 1 row 0, x. Basically what that means is that you know what, let's look at the I have something called tables here, map tables and screen tables. Now these are not tables like we're used to, so these are not real assembly tables. These are just some labels that I made, which means they're not going to take up any space. So why did I do it like this? Well, when I write map row 0, 1, 2, 3, all the way down to 24 here, and I say, what is that? Let's look at map row 0, for example. Well, it's map's address. Map's address is where I place my map file in the RAM, the Commodore 64 RAM. So that's where the memory address where that map file starts. Alright, then I say plus map width times 0. Now map width, that's the entire width of the map, which is 256 characters. So this first map row 0, that's just going to be the first memory address where the map is. The second one, called map row 1, it's also the map address, but now we're adding map width times 1, which means if we add map width, that's 256, so it's a full length of the map, which means we're going to end up with the next row below the first one. And we go down like that, just adding a map width for each row, which means we're going to end up with the entire first column of the map. We have every memory address for the first column of the map. And that is our scroll X. If you remember from the last episode, scroll X is basically just the leftmost column of our camera. So what we're doing with this is that we are using either X or Y as some sort of offset, and we need to load every one of these addresses with scroll X as an offset for this. And I do that for the color file as well, because like we saw earlier, the color file is exported the same way as the graphics. And I actually do it the same way with screen RAM. These are not real tables, once again, they're just labels like this. But I set them up here, so screen RAM 1, for example, it's 0400, the screen RAM address, plus 0 times 40, that's the first top left address of screen RAM 1. I'm going to call 0400 screen RAM 1. So, and the next one here is just the row below that, because we are adding 40 columns, which means we are going a full length of the screen, and then we get the next row here on the left side. So now we have the memory addresses that we need. We do the same thing for screen RAM 2 here, which is the 0C100 range. and a screen color RAM. Now I'm sorry that I have a lot of labels here. I know that some people have commented that I shouldn't use so much labels, I should use more actual memory addresses. So I'm sorry about that. I'm gonna try to get better at that. But hopefully you can see the point I'm trying to make here. We are constructing these hard-coded memory addresses. And the point here is that we need to have a system that keeps track of the scroll X thing, or our camera. So we need every single memory address here on the left side, the beginning of the map. And like I said, a full map length is 256 characters. That's how we made the map in CharPad. So the next row here is just 256 down. So that's how we get the leftmost column of the map. And since the X or Y register is like, this is an 8-bit system, so it can have a number between 0 and 255, which means that just using that as an offset, we can have this column go all the way across the screen like that. But then the next question becomes, alright, so we see this nice yellow frame here, which I said was our camera, but that, I just said that we have just a column. That's not a camera. Well, that's the whole thing here. The camera is just something that we have to imagine. We don't really have a camera like this. We just have these memory addresses that's going to construct the leftmost column. And just by making a routine based on that leftmost column and those offsets that we have using the X or Y register, so for every one of those memory addresses we can read actually 39 characters. A full screen is 40 characters. Now we have adjusted the visible area to 38 characters, but we need to load the part of the map that's not just 38. We need an extra column to the right behind the hidden border on the right side of the screen, because it needs to be there. So when we are adjusting the screen to the right, we are the hidden part of the map on the right side of the screen will slowly be more and more visible. So we're gonna have to load not the full 40 column screen, because it's not any point to load the leftmost column behind the hidden column on the left side, because we are not just scrolling left, so we can save some time by not loading the leftmost column, because that's hidden anyway and we're scrolling in that direction. But on the right side there needs to be graphics behind that hidden column on the right side. Since we're scrolling there, the graphic needs to appear from behind that hidden column on the right side of the screen. Again, I know this is complicated, but hopefully this makes some kind of sense. The point here is that we are doing this for both the map graphics and for this map color file. We're starting with memory addresses that's going to construct the left side. We're doing that for every single row. And just by using this offset, we are reading 39 characters to the right for every single row. And that's, let's see, that's why the code looks like this. We have map row. This is the first memory address. When I say map row, that's the map graphics, comma Y. Now if you look up here, I just loaded Y with scroll X, and we start scroll X with 0, which means in this case map row 0, comma Y, that's the top left corner of the map graphics. And I want to store that, let's see, yeah. I want to store that into screen RAM 1 row 0, comma X. Now comma X, this is just a loop that I made. It's going to go 40 columns, or 30 39 columns over. So if we look at my code here, try to look at everything at once. I have LDA STA, LDA STA. I have that 25 times down from 0 to 24, which means that I'm reading from the map file, storing to the screen, reading from the map file, storing to the screen, reading from the map file, storing to the screen, for every row like that. That's one column, reading a column from the graphics file, storing that column to the screen. And comma X, so we have two offsets here. We have the Y, which is, we keep track of that using this scroll X variable. So I do this because X and Y is not, it's going to be different. So we need to make sure that scroll X is, that in this case Y is always scroll X, because like I said, it's our camera system. But when we're using the X register, it's this loop here. This is just a simple loop, right? I'm loading X with 0. Then I have load map calls on screen 1. And then I have this LDA STA all over again. And then I increment Y and increment X. Y is scroll X. But the X register, that's just this counter for this loop. And like I said, we do that 39. So imagine we have this column where we're reading from the map. We are doing it very brutally here, brute force. We're reading and storing for this entire column. And we have this loop, which means that we can move that, read and store that full column from the map graphics, reading and storing it to the screen. Like I said, it's hard to explain this stuff because it's kind of complicated, but hopefully it makes some kind of sense. And the thing is that, like I said, we could have made some sort of fancy thing here where we have the branching, subroutines and all sort of things here, but that would be way too slow. We need to make this, use brute force here, just LDA STA, because that's much faster than having a lot of loops and subroutines going in the background. So I actually have one subroutine for doing what I said, loading and storing for screen 1. And I have the same thing for screen 2. Screen 1, that's the 0400 area. Screen 2, that's the 0C100 area. And I also have some sort of sprite graphics in here. Let's not worry about that because that's just some extra flavor to this whole thing. But even though at first glance this might look intimidating, the code itself is really not that complicated when you start to look at it. Like I said, a lot of it is just LDA STA, and we use that all the time anyway. So we need to do a few things here, and the key memory address is D1016, screen control 2. So the first thing I do, like I said, is just when we're adjusting the screen, we are checking, are we halfway across the screen? Okay, if we are halfway across the screen, then we need to load the next part of the map to whatever screen is not active. And that would be either screen 1 or screen 2. And that's why I do this thing that I talked about earlier with scroll X. And this is just a nice way to either get a 0 or a 1 based on this scroll X value. So I load that, but then I continue on. So we have shifted the screen over 4 pixels. We got halfway, then we loaded the next part of the map to the other screen, the inactive screen, and then we continue on here. And again, we load D1016. We mask off these scroll bits, and I say compare with 0. Now, if you've programmed in assembly language for a long time, you know that we don't have to write compare with 0, but I do it in this case just to make it more clear what we're doing. Why am I comparing with 0 here? Well, like I said, in the beginning. We adjust the screen from 7 to 0, 7 to 0, 7 to 0, 7 to 0. That's happening all the time. So what happens when you get to 0? That means we have adjusted the screen all the way to the left. What's going to happen then? Well, first of all, if we haven't reached 0, if we haven't adjusted all the way to the left, then we decrease D1016, which means we adjust 1 pixel to the left, and then we just RTS exit this whole routine. So that's going to just allow us to actually adjust the screen. So this is the actual adjusting the screen. Just 1 pixel, right? So, and then we exit. And the next time when we get here, adjust the next pixel. Exit. And next time we get here, adjust the next pixel, and so on. But at some point we get to 0, which means we have adjusted the screen all the way to the left, and that's when the next part of the code happens. Don't have to worry about this that I've commented out. Actually, right now we can just delete it just to avoid confusion. But when we have got the screen adjusted to the left, then I say reset scroll map left. I reset scroll bits in D1016 to 111, which is 7, which is bang. We quickly just bang adjust the screen over to the right side of the screen so that we're ready to scroll it left again, or adjust it left again. So we just put the screen all the way over to the right, and we do that just using this OR command. We load D1016, we just OR those 3 bits, which means set those 3 bits to 1. And when we've done that, bang, quickly change over to the other screen RAM, the inactive screen RAM that we just loaded the next part of the map on, because that's why we did it earlier, so that screen will be ready. Now we're switching over to the inactive screen RAM, which is going to be either 0400 or 0C100. Remember, we're juggling between those 2 screen RAMs. And the way I do this is again by using scroll X, the variable, with this little bit here on the right. Like I said, it's always going to be either 0 or a 1. That bit is always going to be 0 or 1. Then I say transfer A to X, which is now I have either a 0 or a 1 in X. Then I load D1018, which is screen memory setup, that memory address. And I just want these 4 bits in D1018, which is why I write AND here, just to mask off those bits. And then I say OR with a little table that I have here, screen memory setup table. Now, this is just a very tiny table that I made with 2 entries. This one and this one. And those are just the 4 bits that set screen RAM to either 0C100 or 0400. Actually, let's see. Yeah, we're here. I'm not sure, but in case I said something wrong, I need to correct myself now. I set these 4 zeros here to make sure that when we're loading D1018 and I say AND with this number, basically I'm zeroing out those 4 bits. We're loading whatever's in here, we're ANDing it with this number with 4 bits over there, which is clearing those bits. We're not saving anything to the memory address, still in the accumulator, but we're only interested in preserving those bits. Why am I doing this? Well, because in the next line here, I say OR with whatever I got from screen memory setup. Oops. This table, and it's going to be either that or that. Those bits. And that's what I store back into the 2018 screen RAM. So in other words, in simple terms, this little code here is just switching between 0400 and 0C100. That's what this stuff does. Right. And then I have this little coloring routine here. Color the map. And it just works the same way that I explained with how the graphics was being updated. We just have this simple loop here that's going to go from 0 to 39. Why? Well, because we have 39 columns. We don't care about the leftmost column, that's hidden anyway, and nothing's going to appear from behind that. We are only scrolling in that direction. So 39 columns. And we have a full column here. So basically what we're doing here is the exact same thing that we did when we were painting the graphics. Now we are just doing the same thing with the color file, the one we exported from CharPad. So we're doing the same routine. That's why I have this camera there as well, because we need to read from the same position. Let's say scroll X was 5 right now. So if scroll X is 5, that means camera has shifted a little bit over. Then if we're reading graphics from the area where scroll X is 5, then we need to read the color information from that same offset, so that the colors correspond with the graphics. And that's just a coloring routine. And we do take that whole column, just swipe across the screen, loading and reading 39 times, so that we cover the screen like that. Yeah. So basically that's it. Now it's really tough to explain this sort of thing, but hopefully you can see the big picture here, what's actually happening. Like I said, we don't have any fancy yellow camera that moves across the screen, but this little routine where we have this loop that goes over, we have this column that's going to move 39 times across that, like that. That's going to give us some sort of camera system. And combining all of these things, adjusting the screen, making sure to load on the inactive screen when we're halfway, scroll the next part of the level, switch over to the other screen, and quickly color the screen and start adjusting again, and doing that all over and over and over again. And that's going to give us scrolling. So that's it. Now it's really tough, like I said, to explain a complicated topic like this. And it was really hard to try to make a piece of code that's as easy as possible to understand, that also works. But hopefully watching these videos and studying the code I'm going to give you will give you some kind of understanding on how we can make scrolling work. So I hope you got something out of this and that it made some kind of sense. But, you know, that's it for today, and that's it for our scrolling series. So have a great day, and I'll see you in the next video. Bye bye.